Okay, let's just dive right in. For years, artificial intelligence has kind of felt like a giant brain without a body, right? I mean, it's processing massive amounts of text, generating crazy images, and crunching endless data, but it's been completely trapped behind a screen. Well, in today's explainer, we're going to unpack the physical AI stack and see how we are finally training embodied intelligence. It is an absolute paradigm shift in how machines interact with the real world.
So take a second and ask yourself this. Could a robot learn to weld just by watching a human do it once? Historically, getting a robot to weld meant spending weeks writing hundreds of lines of rigid code, calibrating exact spatial coordinates, and painstakingly troubleshooting every single minor physical deviation. But what if you could just watch a human and instantly mimic that action? Well, that introduces the completely game-changing solution of training by demonstration. To understand exactly how this works, here is our roadmap for the explainer. First, learning by watching. Second, the physical AI stack. Third, from simulation to reality. Fourth, standard bots in action. And finally, the future of programming.
All right, kicking things off with part one, learning by watching and the rise of embodied intelligence.
So, what are we actually talking about here? At its core, embodied intelligence is basically machine learning that bridges that massive gap between digital processing and physical robotics. The crucial point is that it's not just thinking anymore. It's physically acting out in the real world. We are asking a machine to step up and master high-stakes manual tasks like precision welding or heavy industrial palletizing. Now, this brings up a really vital distinction in modern robotics. On the left, we've got intelligence augmentation, or IA. That's basically just enhancing human capabilities with power-assisted tools. But on the right, that is true artificial intelligence in a physical form. It's the huge leap from simply giving human workers better tools to building machines that can observe, learn, and then physically act completely autonomously without a single line of traditional code. Moving right along to part two, the physical AI stack, looking at the brain and the body. Think about it. You absolutely cannot have a robot pausing to buffer while a heavy, dangerous object is falling on the factory floor, right? So we rely on a very strict separation of powers here. Up in the cloud training loop, you have this massive processing power handling global learning, essentially the heavy lifting of the AI's brain. But running directly down on the robot itself is the local inference engine that handles the lightning-fast real-time physical execution. The heavy learning happens way up in the cloud, while those split-second reflexes rely entirely on the local engine. Which brings us to part three, from simulation to reality, also known as the digital dojo. Okay, before this AI even moves a physical robotic muscle, it goes through what we call the learning loop. It basically grinds through millions of digital practice reps in a simulated matrix, using environments like NVIDIA Isaac Sim. It trains heavily on synthetic data, meaning millions of varied, artificially generated scenarios. Then, when it finally enters the real world, it relies on continuous, vision-based self-correction to constantly refine those physical movements. But, and this is a big but, we hit the messy reality pitfall. Look, an AI model can pick up a digital widget flawlessly a million times in a row inside a simulation. But messy reality? It throws curveballs. Something as incredibly simple as a passing cloud casting a shadow on the factory floor can literally derail a robot's vision sensors entirely. Actually, bridging this unpredictable sim-to-real gap is easily the absolute hardest part of embodied intelligence, because as it turns out, the real world is a heck of a lot less organized than a server rack. Let's see what this actually looks like in practice with part four, standard bots in action, focusing on the RO1 cobot. To really ground this theory, take a look at the standard bots RO1. This is a 6-axis AI cobot, and the real standout feature? Zero code required. None. It totally ditches the old traditional programming model. Instead, this thing operates on GPT-4 level logic. You can literally just physically guide the arm or let it watch a human perform a task, and it learns the whole shebang entirely by demonstration. It understands the goal, maps out the action, and instantly translates that into smooth robotic movement. And get this, the result of that learning by demonstration? A repeatability of plus or minus 0.025 millimeters. I mean, wow. That insanely precise repeatability is the absolute wow factor here. We aren't talking about a robot vaguely mimicking a human waving. We are talking about an AI observing a task and then executing it with microscopic, razor-thin precision. It absolutely proves just how much physical mastery an embodied AI can achieve today. That pinpoint accuracy is exactly why this tech is becoming absolutely critical for heavy industrial tasks right now. It completely masters precision quality control, actually using its vision to inspect parts way faster and better than the human eye ever could. And for heavy-duty end-of-line palletizing, a cobot trained by demonstration can just stack heavy boxes flawlessly, 24 hours a day, dynamically adjusting on the fly if something is placed even slightly off-center. It's a total game changer.
Finally, let's wrap things up with part 5, the future of programming, looking at the risks and realities.
So what's the catch? Well, the biggest hurdle we face right now is the black box safety dilemma. See, with traditional coding, if a robot makes a mistake, an engineer can just go in, look at the code, and find the exact line that caused the error. But these AI models, they are often non-transparent black boxes. We know exactly what data went in, and we know what physical movement came out, but we don't always know exactly how or why the AI made its decision in the middle. We really have to ask ourselves, can we truly trust these black box models when they're operating super heavy, high payload machinery in dangerous environments alongside human workers? Which leaves us with this one massive, provocative question. Does physical AI mean the absolute end of traditional robot programming as we know it? Think about it. If a machine can simply watch a welder, deeply understand the intent using GPT-level logic, and then execute that exact task with microscopic, perfect repeatability, well, why would we ever sit down and write rigid manual code again? This monumental leap from the digital cloud straight into our messy physical reality is happening right now. Are we ready for a world where we no longer program machines but simply show them what to do?